So what we're looking at next is symmetry. And the idea of symmetry is, well, it's this idea of reflecting a function across an axis. And to give an idea, for example, let's talk about symmetry with the y-axis. A function that's symmetric across the y-axis, a good example, y equals x squared. So what this does, it's a mirror reflection of itself across the y-axis. And what this really means, if a point xy satisfies this equation, then another point, negative xy, also satisfies the equation. So, for example, if you plug, say, x and y, they're working, they're doing their thing. But if we plug negative x and positive y into this equation, does it simplify down to be the same equation? Does the equality still hold? Does anything change? Hopefully not. So plug in our positive y, and then we have our negative x. We square this, and sure enough, we get the same equation. So this point satisfies this equation. All right. Now let's talk about symmetry across the x-axis. Now this one's a little trickier. What this says is this. Well, it's a mirror reflection of itself over the x-axis. And for this example, you could say we have y equals negative square root of x. And this would be y equals positive square root of x. And that would be negative square root of x. Now what it's saying is this. A point xy means you also have a point x negative y on here. So if this satisfies the equation, well, then this will satisfy, well, in this case, it's not really an equation. This will satisfy whatever relation that we have. So you could test this in some way. For example, if positive x and positive y are working here, square root of this gives you that. Well, then that means the square root of this would give you negative that. So we can substitute in, put in negative y equals to the square root of that positive x. And then we get negative y square root of x, divide that negative over, and we get y equals negative square root of x. So this point does work for this part here. So that's the idea of symmetry across the x-axis. If you have x and y on your plot, then x negative y will also be on your plot. Let's look at the origin. Now, for the origin, sort of the canonical function we use for this one, y equals x cubed. So what this one says, if x comma y satisfies the equation, then so will negative x, negative y. That'll also satisfy the equation. And you can test this. Say we have y equals x cubed. We have an x and a y that make this work. So what happens if we substitute negative x and negative y? Do we get the same equation back? Well, we have negative y, negative x cubed. Well, this is just negative y. You cube a negative, still comes out negative. Even powers, apply the negatives, make the negative go away. Odd powers, you'll keep the negative there. And if you multiply both sides, say by -1, sure enough, this simplifies down to give you the original equation. So this point does work. Now, as far as reflections go, it's sometimes mentioned is the way you handle reflection of the origin is you can reflect across the x-axis. If you did that, you would get this. And then reflect this over the y-axis. And that's the idea of you'll end up getting this overlapping. You do this and then do this. This will overlap on that. And that's oft sometimes cited as what reflection across the origin could mean. Anyways, look at some examples. All right. So let's say we have something like this. Well, what kind of symmetry does this have? Well, let's test y-axis. So y-axis means if xy satisfies the equation, then so does negative xy. Well, is this true for y equals x squared minus 2? Well, let's substitute negative x comma y into the equation and see if it simplifies to stay the same. So we have y equals negative x squared minus 2. Square this. Y is x squared minus 2. And sure enough, simplifies to be the same. So this is symmetric across the y-axis. Now that doesn't mean that we're done. You could have multiple symmetries. For example, if you take the circle would be symmetric across, if it's centered at the origin. A circle centered at the origin is symmetric across the y-axis and across the x-axis and across the origin. Borrowing some artistic license. So as for symmetry across the y-axis on a circle, sure enough, we do get this. And for symmetry across the x-axis, well, we certainly do get this. And then for symmetry across the origin, we definitely get this. So a circle is symmetric across the x-axis, y-axis, and origin. So what this means is we want to test all of our symmetries on this equation to see if there's others that work. And some equations, none of them work. So let's see. X-axis. XY. Is something symmetric across the x-axis if xy satisfies the equation? X negative y satisfies the equation. So let's see if this works. Negative y is x squared minus 2. Again, the x doesn't change, but the y takes on negative. So we get negative y is x squared minus 2. Multiply through by -1. This will become positive. This will become negative. And then negative times negative becomes positive. And what we get is something different from what we had before. So this means this is not symmetric across the x-axis. Let's try origin. So y-axis so far so good. If xy satisfies the equation, then negative xy should also satisfy the equation. Well, let's see. That means you replace y with negative y, negative x with negative x. Does this work? We have negative y is x squared minus 2. Again, squaring a negative makes it go away. Multiply through by negative 1 to get positive, negative, and positive. Trying to make this y positive. But what I do to one side, I got to do to the other. I multiply this by negative 1, then I multiply this side by negative 1. Negative end up distributing the negative 1 to get negative x squared. Negative times negative is a positive. And again, this doesn't match. You might have seen that already up here, but again, this isn't working. So this is not symmetric across the origin. So the symmetry that we can show is that it's symmetric across the y-axis. And there we go. We can prove that much. All right. Let's do another one. Let's see here. Let's say we have this. What about this? What's the symmetry here? Well, it doesn't look like a function necessarily, but that's okay. We're not going to demand that we could solve for y in this case. We just want to make those substitutions and see if they simplify to give us the same thing, at least what we started with. So again, for y-axis, if xy satisfies the equation, then negative x comma y will too, if it's symmetric across the y-axis. So that means we'll get negative x squared y squared plus 5 times negative x times y equal to 2. Square this, x squared y squared. Well, so far so good. Looks like it's working. But here, 5 times negative x, negative 5xy equals 2. We get a different equation from what we had before. So this doesn't work. It's not symmetric across the y-axis. All right. So let's try this one. X-axis. So with this one again, if xy satisfies the equation, then so should positive x, negative y. That should also satisfy the equation. And if we substitute this in, we'll simplify. We'll get the same thing we started with. Well, let's see. Well, x squared negative y squared plus 5x times negative y. Let's simplify this, see if we get the same equation we started with. X squared y squared. And again, we're going to get minus 5xy is equal to 2. This is not what we started with. So we don't have symmetry across the x-axis. There's one more to try. And again, they might not be symmetric at all with any of these symmetries. Maybe we'll still get the origin, though. Let's find out. So for origin, xy becomes, well, if xy satisfies the equation, so does negative x, negative y. So negative x squared negative y squared plus 5 times negative x negative y is equal to 2. Will this simplify to give us the original equation? Well, negative squared is, well, that negative goes away. Negative squared, again, negative goes away. Here, negative times negative is positive. We get 5xy equals 2, and sure enough, it's the same thing that we started with. So in the end, this is symmetric about the origin. And there you go. Now, related to this is the idea of even and odd. Even odd. And what basically an even odd function is, an even function, it's symmetric across the y-axis. Another way, again, saying that if xy satisfies the equation, and so does negative x, y. Another way of saying this, if I have f of x, and I put x into f of x, then if this satisfies the equation, so does this. This will also satisfy the equation. X and x, the y value, and the y value f of x. Negative x, y value, and then this negative x will simplify inside f of x to give you the, well, the f of x. Let me explain that a little better. What they typically say is this. If you're symmetric across the y-axis, if you're an even function, then f of negative x will just give you this. If you might be wondering, well, why don't you put negative x in there? Isn't that what you have? And you're right, we do. But when you plug negative x into f, it'll simplify to just f of x. The minus sign just disappears. So f of negative x will equal f of x. So an example of this is y equals x squared. And one way you can remember this, we'll say f of x equals x squared. The way you can think of this being even is, think of the sort of canonical example of a even function. That's what f of x equals x squared is. It's got an exponent of 2, which is an even number. So watch this. Let's say this is our function. Well, then if we put in negative x, what happens is we're going to square that negative x, and that becomes x squared. Because when you square a negative, it goes away. Well, x squared is just f of x. And so sure enough, f of negative x becomes just f of x. So that's the idea of an even function. You put in a negative version of x, doesn't change anything. All right. Look at odd. So this is symmetric. Across the origin. When it comes to even and odd, we skip the symmetry across the x-axis. The reason is when we're talking about functions, symmetry across the x-axis means you're not a function. So, and that's fine. You can be what's called a relation. But if you have something like this, barring artistic license, this is symmetric across the x-axis. It's a reflection of itself across the x-axis, mirror reflection. And if you put a vertical line through here, it fails the vertical line test. In other words, it's not a function. We're only interested in functions at this point. We're talking about even and odd. Again, just to review what's so significant about a function, the problem with this is if we put in a value x, what's the value of x? Is it this or is it this? Is it this? Is it this? And this is what we call ambiguity. If I have an input of x, I'll get an output of y or maybe an output of negative y. Well, which one do I get? And functions are special types of mathematical relationships where every input has only one output. You can think of it as like earning wages. If you work 10 hours and your shift manager says, well, if you work 10 hours, you get $100. And then another shift manager comes on board and says, if you work 10 hours, you get $50. Well, wait a minute, how much do I make? With a function, there's only one output for your input. When you put in 10 hours, the first shift manager says you make $100. The second shift manager better also say you're going to make $100. There's only one output for the hours you put in, and that's $100. When something's not a function, you can have two different outputs. So functions, we limit it to one, and that means we can't do stuff like this, and we're not going to deal with symmetry across the x-axis. Anyway, little digression. Back to symmetry on the origin. Well, that's what an odd function is. And that means if xy satisfies the equation, so does negative x, negative y. So in an example, what you'll usually see is this. If x, f of x, satisfies the equation, then so does negative x, negative f of x. That will also satisfy the equation. Now where this is going is this. If you input x and get f of x, this means inputting negative x gives you negative f of x. So f of negative x, we put this in the f, we're actually going to get this. And that's what an odd function does. So there's sort of a canonical example that goes with this. Let's take a look at x cubed. A little more real. So here we have x and f of x being a point on the plot of this function. Let's plug in negative x. So f of negative x means negative x cubed. And remember, when we cube a negative, the negative is still there. We get negative x cubed, which is negative x cubed, applying a negative sign to the function x cubed. But x cubed is f of x. This is negative f of x. And that's how that one works. In a way, you can remember that this is odd. Look at the power on the x. It's an odd number, a cube or a 3. So that's the idea of odd and even. Now let's take a look at an example. Let's say we have something like this. So let's figure out, is this an odd function? Is it an even function? Could it be neither? That's a possibility. So let's take a look. Let's test if it's odd. If it's odd, well, actually, no, I'll take this back. When we test for even and odd, we're just going to do one thing. It's not like the symmetry test we just did. If you notice for even and odd, each time we insert a negative x. And we're going to look for an outcome of either f of x, which is even. We could get negative f of x, which is odd, or we might get something else that's not this. We don't get the original function back, nor do we get the original function just multiplied by -1. We might get neither. But where this always starts, put in negative x. Let's see what happens. So f of negative x. That's negative x squared minus negative x to the fourth plus 1. Now, when you take even powers, like you square a negative or have a negative to the fourth, even powers make the negative go away. So we're going to get just x squared minus x to the fourth. This is outside the fourth here, so it stays. And we get plus 1. And if we look at this, this is the original function, which is f of x. So an f of negative x gives you f of x. That means even. Let's take a look at another one. Let's try this. So for this one, I get f of negative x. Well, if we do that, we get negative x cubed minus negative x. And when you cube a negative or apply an odd power to a negative, the negative stays there. So you get negative x cubed plus x. Ooh, what's going on here? Well, what you can do, we can actually factor out a negative. Take this a step back a little bit. This is minus a negative. So we have a negative on x cubed, a negative on x. Let's factor out that negative. Here's this minus sign. Here's x. We pulled the negative off here and the negative off here, factored it out. And if we look at this, well, this part here is our f of x. So what that means, we have negative f of x. This here, that's familiar. So what this says, if we have f of negative x, and it gives us negative times f of x, that means odd. So this is an odd function. All right. Let me check something here real quick. So we got some extra answers here. I just want to make sure. We'll do another one of these real quick here. Let's check in. So what they were doing is they also wanted you to test symmetry. And again, if something's odd, that also means it's symmetric about the origin. If it's even, it's symmetric across the y-axis. All right, let's do another one. Let's say we have this. Again, we're just going to plug in negative x. So if we square this, negative goes away. We get x squared minus and minus is positive x. So what's going on here? Well, first off, this is not the same as this. So it's not equal to f of x. We need a minus here to be equal to f of x. We can try to factor out a negative. We could say this is a double negative, and this is a double negative. So we can factor out these negative signs, because negative and negative is positive, negative and negative is positive. Let's factor out this negative. We get negative x squared minus x. And this is not equal to f of x. Remember with odd, you'd have negative and then f of x in here. We're close, but we've got an extra negative sign. So it doesn't work. So it's not going to be f of x. It's not negative f of x. This is neither even or odd. And sometimes that happens. All right. Now, something else they bring up in the text here, and this is sort of heading towards calculus, and it's an idea called difference function. And the way a difference, and we'll get to piecewise functions, we certainly will, but it's called a difference quotient. And what this is, it's kind of a composition. You take a sort of a simple function, x plus h, and you insert it in the f. And it works like this. Now, why would you study something like this? It's, again, something that comes up in calculus. And it has to do with something called a derivative. And the way this works is, we'll have to show you how it works, but I'll draw a picture here. Let's say we have our function f. And let's say this is x. This is x plus h. So this would be f of x. And this is f of x plus h. Now, what you would do here is, if you draw a line between these 2 points, it cuts across this function f of x. Cuts across like that. And this is what they call, say, a secant line, at least when you talk about circles, where you intersect a circle at 2 points. You're getting a secant line. And usually with secant lines, they usually don't have them pass through the diameter, but anyway. What we might be interested in is a tangent line. And a tangent line is where this line, if a line contacting this graph at one point. So the way you could do that, let's say we have this h, and let's shrink h, because the distance between here and here is h. Let's make h smaller. Like let's say let's go half of h. Let's shrink h in 2. So now x plus h is right here. Well, now you draw your line. It is still intersecting the graph at 2 points, but this point's a lot closer. In fact, what happens if we make it really close? Let's really shrink h. Put a line through here. If you notice what's happening, as h shrinks, the distance between here and here gets smaller. This point gets closer to that point, and we get some kind of idea of what a tangent line, you get a line that contacts this function at one point. There we go. A tangent line contacts this curve at one point. And as this point gets closer to that one, we start to see what the tangent point's going to look like. Sorry, tangent line when it's crossing this curve at one point located here. Finally, in theory, if h is 0, we would get a tangent line that looks like that. And my drawing doesn't really do it justice. Contact just at one spot, like so. So the reason we use the difference quotient is it's going to let us create, ultimately, this tangent. Now what's going on here? Technically what we're actually doing, this is the slope of the tangent line. We'll talk about slope a little more, but we're going to find the slope of this tangent line. Go back here, x plus h. This is f of x plus h. So the line passing through those 2 points, we compute the slope m, y2 minus y1, x2 minus x1. y2 will be f of x plus h. y1 is f of x. And then x plus h is x2. And then x is, well, x1. Well, here you have x minus x. You have x of x plus h minus f of x over just h. So what happens here? This difference quotient is really the slope of a line cutting through these 2 points. In calculus, we're going to have this h go to 0. And this point's going to get closer to this one, creating a tangent line. In other words, a line that contacts this curve only at one point. But that means if we take our difference formula, difference quotient, which is the slope of this line, if we let h go to 0 in our difference quotient, we're going to get the slope of that tangent line contacting the curve at that one point. Anyway, that's what this whole difference quotient is all about. Moving on. So let's do some examples with it. And we'll play around with some calculus too. So let's say we have this. Let's compute the difference quotient for that. Well, difference quotient, x plus h minus f of x over h. So we take x plus h Substitute that in for x, we'll get 4 times x plus h instead of 4 times x minus f of x, which is just 4x over h. So we simplify, we'll get 4x plus 4h minus 4x over h. These are going to cancel. We'll get 4h over h and 4. And so it simplifies to 4. Now in calculus, what you'll do is you'll shrink h down to where it's practically 0. And practical is kind of the key thing here, because if you actually let h be 0, you're dividing by 0, and that you can't do even in calculus. But we say h is practically 0, and if it's practically 0, you can divide by it. These will cancel out, and you get 4. So there aren't any h's when you simplify down. So if h is practically 0, well, this is still 4. What this will tell us is that when we make h practically 0, the slope of the tangent line is going to be 4. If you think about it, that kind of makes sense. Because if you graph f of x equals 4x, well, it's a line. So any line that contacts it at one point, well, going to have the same slope, actually. You could argue that you could rotate this around, but maybe this isn't a good example. But ultimately, what's going to happen if you have your x and your x plus h, as h shrinks, this point, you're going to be drawing a line through these 2 points. And as this shrinks down, you're still drawing the same line. So when h is practically 0, you're still drawing through those 2 points parallel and on top of this line. So oddly enough, your tangent curve actually sits on top of your curve, which is usually not what we mean by a tangent. A tangent is when it contacts the curve only at one point. So let's look at an example where that happens. Let's say we have this. Let's compute the difference quotient for this. So again, you have f of x plus h minus f of x over h. So for this, we're going to replace x with x plus h. So you have x plus h squared minus f of x, which is still x squared, over h. FOIL this. X squared plus 2xh plus h squared, and then we have our minus x squared. Let's squeeze this in here. So x squared plus 2xh plus h squared, and then we're still subtracting the x squared, divide by h. And you can see that the x squareds here, positive and a negative one, they're going to cancel. 2xh plus h squared over h. We can factor out the h. You get h 2x plus h over h. The h's will cancel, and then you'll get 2x plus h. And that's your answer. So here, there's a couple things going on. We're going to go back into calculus. We've got our curve. And so you would have a tangent, unlike the line, where your tangent only contacts this parabola at one point. Does this. So when we do the calculus part, we let the h practically become 0. So basically what we get is 2x is the slope of this line. Usually slopes are just numbers. How can a variable be the slope? Well, what it is, in this case, the slope depends upon the x value. For example, if you have a tangent here, at the origin, what's the slope of this horizontal line? Well, the slope of the horizontal line is 0. So if we look at our formula, that means if we put in x is 0, because that's the x value at the origin, 0 times 2 is 0, well, that matches up. The formula for our slope is going to be 0 at x equals 0. And sure enough, that's what we get for a horizontal line. So this is a formula for the slope of tangent lines all along this parabola. And to find out the slope, put in the x value of the point where the tangent line contacts the curve. And you take that x value, plug it into this little formula, and that will give you the slope of that tangent line. So for example, if this was x equals 3, then the slope of this line would be 2 times 3, or 6. So that's the idea of a difference quotient. Now for our class, we just have to simplify and we're done. We don't have to do it in calculus, but that's ultimately where the difference quotient comes in. All right. So the last thing to mention, piecewise functions. And where piecewise functions come in, we have sort of canonical functions. For example, we might have lines. So y equals mx. And we can do mx plus b. We have parabolas. And you can modify these. You can translate them. You can flip them down. So y equals x squared. We have the cubic equations, cubic formula. We have, say, the absolute value. We have horizontal lines. Y is equal to a constant. Let's see, square root. And we have a cube root. So these are typically the functions that we play around with. We'll play with versions of these. We might translate these to the right, translate them to the left, have them move up, have them move down. We might flip them, reflect them across axes. But we start out learning these kinds of functions, and then, well, we can do different things with them. But sometimes things can change. We might need something more complicated. And when we start out with a function, we might discover, well, it's too simple. We need to add some more detail, especially if we're using our function to describe a relationship. So let's say we have something like this. Let's say you're working at the subway and you open the door at 8 a.m. and there's nobody there. But then from 8 a.m. to 12, there's always someone in line, and someone comes in, excuse me, someone comes in while you're making a sandwich for somebody else. So you finish their sandwich and they leave, and well, then someone else comes in again. So it's like you have 4 people in the store and you make a sandwich for someone, they leave, you're down to 3, but then someone else comes back in, you're back to 4. And so you notice on average, say per hour, you start at 0, and then by noon, there's an average of 5 people in the Subway store. And then from noon to 2, it stays that way. On average, there's always 5 people in the store per hour. So what's happening is, well, we've got something that looks like it's a line, like y equals x or y equals mx plus b. And then we have a constant here. Now, how do we come up with something like this? So what we can do is we need to come up with what's called a piecewise function. So we only need a piece of, say, y equals mx plus b, and then we need another piece of, say, y equals 5. And so we're going to stitch these pieces together to give us a more detailed picture of what's going on. So let me run through an example. Let's say we have this. So let's see the function of this. And keeps going. So the way the text goes about this is this. We're going to use inequalities, and we tend to use the equal to inequality for where a function stops, and we're going to use the inequality, say, let me see here, I'll make this keep going this way. That. We'll use the equal to inequality where a function stops, and we use, say, the greater than where a function starts up again. So what's going on here? Well, here we've got the function y equals x. 1 and 1, 2 and 2, 3 and 3. This is y equals x. And here we have y equals 3. So how can we describe this as a piecewise function? So what we say is this. F of x will be a piecewise function. Now, the key location in this is the 3. Out here, we're just using y equals x. Out here, we're just using y equals 3. Where things change is at x equals 3. So it looks like this. we have two intervals on the x-axis we need to account for. First one is going to be x, c, less than 3. So it looks like the book's doing something different. Where a function stops, it's using the regular inequality. And then where it starts again, it uses the equal to. So again, where it stops, use the hard inequality. When it starts up again, we're going to use the equal to inequality. So this interval here is less than 3. And then this interval here, there's no hole, so we do need to include 3. X greater than or equal to 3. It would just be greater than 3 if there was a hole here, but there's no hole here. So what's happening for x less than 3? On this side, what are we dealing with? Well, we're dealing with y equals x, or the function x. And what are we dealing on this side? Well, it's just 3. So that's how we would describe this function. Let's take a look at another one. What's going on here? Let's look at this in terms of pieces. Our first piece is x squared. And then this piece here is, say, y equals x. And then this piece here is y equals 3. So this piecewise function has 3 pieces. That means we got to deal with 3 intervals. First interval, we see a change at 1. So that means we're going to consider everything below 1. This is our first interval. So our piecewise function f of x. Let's consider everything below 1. What's going on here? Well, this first piece on this interval, it's x squared. So that's what we've done. Now what? Well, for the next one, it's an interval because we get the next change here at x equals 3. So now we have this interval to deal with. And again, we're going to use the soft inequality, and then where it starts, and the hard inequality where it ends. So what's going on here? Well, over this interval, we have this piece, y equals x. So the function is x. And then for x greater than or equal to 3, again, this is where we're starting. But we have 3. That's what this piece is. And that's your piecewise function. All right. So let's take a look at something else. Let's say we're asked to graph some of these. So let's say we have this. F of x is negative x when x is less than 0. And then it's regular x when x is greater than or equal to 0. How do we do this? Well, let's take a look at our number line. Let's start off particularly with an interest in 0. Now we've got our y-axis. We can put that up here too. But the key thing is our number line's broken up into two parts. Left of 0, which is this, and then greater than or equal to 0. Let's deal with this one first. So when x is less than 0, what piece do we have? Well, we have a negative x. Now negative x looks something like this. But here's the thing. Negative x will only exist to the left of 0. Can't exist to the right, only to the left. So that means the part of negative x that's on the right of 0, that part we get rid of. So that gives us the graph over this first interval. Let's look at the second. Now the second one is x is greater than or equal to 0. So what piece do we have here? Well, we have f of x now equals x, and that's this line here. But keep in mind, we're only supposed to use this function when x is greater than or equal to 0. We're not supposed to use this once we pass 0 to the left. It exists on the right, but it doesn't exist on the left. So we gotta get rid of it like that. And so what we get is this. This is our piecewise function. And you might recall this is what the absolute value is. The absolute value function is a piecewise function. Let's take a look at another one. So 1/2 x less than or equal to 0, and then 3 x greater than 0. So now they're kind of switching it up a bit. Here now we're going to be ending with an equal and then beginning with an open. But looks like they'll switch that up a bit, and we'll see what happens. But again, the key thing is 0. This is where we're seeing change. Let's take a look at this. There's 0, and there's our y-axis. So when x is less than or equal to 0, we have 1/2 x. So 1/2 x looks something like this. But we only get to keep the part of it along the x-axis as long as x is less than or equal to 0. That means this part. That means the other side. We've got to erase that part where x is greater than 0. This is where x is less than or equal to 0. We'll only keep that part of the function. Now this is where it gets kind of odd. When x is greater than 0, we use 1, 2, 3. F of x equals 3. It goes on forever. Now, we got a disconnect. There's a hole, there's a gap. That's okay. Got to turn to the inequalities. 1/2 x, x less than or equal to 0 means x equals 0 is part of this first interval. So if you plug x as 0, for x, you'll get 0. So that means 0, 0 is part of this curve. Because x can equal 0, so let's just take x as 0, plug it in and get the y value, and well, we get the origin back. So this, and sure enough, this passes through the origin anyway. You sort of saw that. But this sort of does it analytically. And I'll go through that again just to make it clear, or hopefully clearer. So what this says is x can equal 0. So if x can equal 0, when we're working with this function, let's find out what the y value is. Well, the y value turns out to be 0. So that means the point 0, 0 is on this curve. And sure enough, that's right where the origin is, where this line passes through. So since it's included, we're including x as 0, that means that we're including the point 0, 0. I put a solid circle there. Now we get to this. This says f of x will equal 3 when x is greater than 0. That means this line, if we go backwards, it won't quite get to x is 0. Like, here we are, x is 2, x is 1, and we're not going to quite get to x is 0. So what we'll do here, at the beginning of this, since it doesn't include the x value where it starts, it doesn't include its start because it's not equal to 0 and it starts at 0. It actually doesn't include it. Because it doesn't include 0, we have to put a hole at that starting spot. It doesn't actually start there, it just gets really close. So that's something to keep in mind. All right, let me do one more. Let's say we have this. Let's see, is that a -3? Yes, it is -3. There we go. So we have 3 pieces to this function. Break this up. Key numbers, -3. There's some kind of a change going on here. And then 0. I'll put my y-axis in here. So when x is less than -3, it's over here, we have this piece. F of x is equal to 0. Well, that's just a horizontal line along the x-axis. But we're going to stop just at -3. Now, whether we should put an open circle or a closed circle, we'll see. But it does do that. Because anything below -3 is going to have this function of f of x equals 0. Well, let's take a look at this. The next piece is -3 to 0. Now, what piece of our function was here? Well, it's -x. So -x is that function that comes down here like this. But we got to be kind of careful drawing this. we can only keep the part of it that's along this interval. So I can't go past 0. Can't do that. And I can't go past -3. So -3 comes up here. So I got to erase this part here. So that's only the piece of -x I get to keep. And then finally, for x greater than or equal to 0, I'm using this. This is a parabola. And it looks kind of like this. Like, let's say we have -1. This parabola does something kind of like this. And, well, hold on here. I can only use the part of the parabola that's greater than or equal to 0. So this is on the x-axis, greater than or equal to 0. That's all along here. That means I can't use this piece here because this is along the x-axis less than 0. I'm going to get rid of this. So I only get to use half of the parabola. Now, what about endpoints? Well, for f of x being equal to 0, this is only for x less than -3, but it doesn't get to equal -3. That means there's a hole. It's a hole. And then for this one, we can input x being -3. So this value will be a part of this piece. And if you want to check this, we got f of x being -x when x is equal to -3. So it means f of -3 is -3. Double negative is a positive. And you get 3. This point here is -3. If you were interested, if you wanted to know. But then x can't equal 0. So as we get close here, once we get to x is 0, whatever point on this line is above x0, got to put a hole. Now this line actually crosses through the origin. So we'll just put a hole in the origin. But let's say we weren't supposed to go to x is -2. That means whatever point on this line is above -2, if we weren't supposed to get this far, we put the hole right there. But in this case, we go -3 to 0, which includes -2. So we do that. And finally, for the parabola, it does include 0. So f of 0 will equal 0 squared minus 1, 0 minus 1, or -1. This will be a point on the parabola. Remember, this is the 0 at the origin. So this would be the graph of our piecewise function f of x. So that's it for this section. If you have any questions, let me know. Other than that, have a wonderful day.